Greetings everybody, and today we're going to be taking a look at some basic properties of rings. So in the previous video we took a look at the definition of a ring as well as some examples. We have these axioms over here which define what a ring is, and from these axioms we can deduce some very basic properties that we're used to seeing from primary school algebra, and these also carry over to rings as well. Now, not all the properties that we're used to seeing from primary school carry over to rings, but the ones I'm going to state here definitely do. These will seem very trivial though, but they're not in the axiom, so we do have to prove them before we can actually use them. So let R be a ring, and as I remarked in the previous video, you can refer to a ring just by the name of the set. So here R is the set, and we're going to assume that it has some kind of addition and multiplication operation on it. We're also going to let A, B, and C be elements of this ring. So let's state a few properties. First of all, if you have A plus a B being equal to A plus a C, then B must be equal to C. Basically, you can cancel the A's on both sides. It's very trivial, and you can prove it from the axioms quite easily. The second property, and this is even more, silly, it says that if you have 0 times any ring element A, this is just going to give you zeros. Very trivial. It's not in the axiom, so again, we do have to prove this. The third property says that if you have a negative 1 times A, well, you guessed it, it's just equal to negative A. So let's just make sense of what each of these symbols mean over here. One, this guy here is the multiplicative identity. And if you put a negative sign in front of a ring element, that refers to the additive inverse of that element. So here, this is the additive inverse of the multiplicative identity. So if you take the specific element over here, which always exists in a ring, using the axioms that we assume for a ring, then if you multiply it by any ring element, that just turns it into the additive inverse of that element. So here it's not negative 1 times A anymore, it's really negative, you put it in front of the A, which really refers to the additive inverse of A. Okay, and the fourth property that I'll discuss in this video is going to be if you have A times negative B, then what you can do is you can bring this negative into the first factor, let's say. So you could have negative A times B, or you could bring the negative completely out of that product there to give you negative of AB. So again, let's be careful with notation over here. If you have a negative in front of a ring element, well, it's not two separate things over here, because, well, negative, that's not really an element. Whenever you see negative in front of a ring element, you should really think about the whole thing together as one, and that refers to the additive inverse of B. And the same goes for A over here, and over here we have a negative of AB, but again, because we have the negative in front over here, it's really this whole thing that's referring to the additive inverse of, well, what's over here, which is A times B. So AB, that's a single element. This is its additive inverse. Okay, so those are the properties that we'll prove today. Let's give their proofs. So for part 1, this one's pretty simple. You start off with A plus B is equal to A plus C, and I'm going to add the additive inverse of A on both sides. So what's the additive inverse of A? It's negative A, so this is one whole element here. You add it with A, and then we still have B still, and this is equal to, well, negative A plus C. Now I should maybe be careful with the brackets as well. Technically I'm doing the A plus B first over here because that's the part that already exists there, and then I'm adding on this additive inverse, and same for the A plus C. And what I can do is I can use the associative laws. So what was the associative law there? It was this A plus, which says you can rearrange the brackets. So by this axiom, we can change the pairing. We can do the negative A and A first, and then we can add B, and the same on the right hand side. Okay, but now, notice that we have an element and we're adding it with its additive inverse. And by the inverse property, so this is the I plus axiom, if you have an element, you add it with its additive inverse, you get just the 0 elements. So both of those guys over there, those become 0, so that we still have the plus B, and then we still have the plus C. Okay, now we can use that neutral elements axiom. So what was n? If you have any element A in your ring, then 0 plus A is equal to 0. So this is what we can apply here. So therefore, we have B is equal to just C. So that proves this first property here. Basically, if you have two elements on both sides of an equation, you can just cancel them without having to do this technical argument every time. Okay, so let's take a look at property 2, which says that if you have a 0 times A, that's just equal to 0. So how can we prove this? I'm going to start off with a very trivial statement, which says that if you have 0 plus a 0, that's just equal to 0. And this is true because of the neutral elements axiom, because here's some element of the ring, I'm adding the additive identity to it, so I should get back the exact same elements. Okay, and what I'm going to do, because I kind of want 0 times a, I'm going to multiply both sides by a. So if you do that, we have 0 plus 0. I'm going to multiply this guy by a, but because 0 plus 0 is really equal to 0, well, that's the same thing as 0 times a. So I'm not using any axioms here. This is something I can do because I'm doing the same thing to both sides of the equation. And now let's use some distributive laws. I'm going to distribute this a into those zeros, so we're going to get 0 times a plus 0 times a is equal to 0 times a. And now I really want to cancel this 0 times a on both sides because I have a bunch of them lying around, and I can actually just use this property that we proved before. Maybe if I want to be extra careful, I should also introduce an extra 0 on the right hand side because there's only one term on the right hand side. So let's do that quickly, and that uses this neutral elements axiom. Okay, so once I have that, by property 1, what we have left is 0 times a is just equal to 0 because, well, I cancel this guy and I cancel this guy. And that proves what we wanted to show. Let's take a look at the third property. So what's the third property? It says if we have negative 1 times some a, that's equal to negative a. Okay, so I want to get this negative 1 somehow. So where's a nice place I can get started with that? Well, I can start off with, again, a pretty trivial equation. Negative 1 plus 1 equals 0. So here, negative 1, that's just one ring element I'm referring to there. And this equation is true because of the inverse axiom for addition, because these two elements are additive inverses of each other. And now I want a multiplication by a into this negative 1. So let's do that. I'm going to take the entire left-hand side, and I'm going to multiply that into a, but this is equal to 0 times a on the right hand side. Now I'm going to use the distributive laws on the left hand side, and I'm also going to use property 2 that we just proved above on the right hand side. So on the right hand side, that just becomes 0, and on the left hand side we get negative 1 times a plus 1 times a. Now 1 times a, we know that's equal to 1 because of this neutral property for multiplication. So we can rewrite this. Now I don't really need brackets over here because it's clear enough that negative 1 we're treating as just one element. So negative 1 times a, we have a plus a is equal to 0. But now what I need to do is I just need to bring this a onto the other side, and I can do so by adding its additive inverse on both sides. So we have negative 1 times a plus a, and I'm going to add the additive inverse of a. And on the right hand side, that should be 0 plus a negative a. So here I'm not really using any axioms, I'm just doing an operation to both sides of the equation. But now we can use the inverse axiom for addition on the left hand side, as well as the neutral axiom for addition on the right hand side. And what does that give us? It gives us negative 1 times a. This part over here, that's just, well, that's a 0. But anything plus 0 is itself, so I'll just leave it as negative 1 times a. And on the right hand side, we are going to have, using that neutral axiom, we're just going to be left with negative a. And that proves property 3. If you have the additive inverse of the multiplicative identity multiplied by any element, that's just equal to the additive inverse of that element. Okay, and we got one more property to prove that for this video. So let's try to prove a times minus b is equal to negative of ab, and I'll leave it as an exercise to show that negative a times b is just negative of ab because the argument is basically identical. Okay, so kind of like before, I see a negative of a ring element here, negative b. So what's a nice way to get that? Well, just like how I want to get to this negative 1 here, I'm going to start off with the equation negative b plus b is equal to 0. So this is from the additive inverse axiom. Okay, but I want an a times negative b. So let's just multiply a on both sides. So we have a, and then we have everything on the left hand side. And this is equal to a times 0. But we proved that 0 times a is equal to 0. But because multiplication commutes, this is also equal to 0. So let's use the distributive laws as well as property 2. And we get a times negative b plus ab, that's just equal to 0. Okay, and here I'm going to treat AB as just an element by itself, and I'm going to bring it over to the other side. So what's the additive inverse of AB? It's negative of AB, because here I'm treating AB as just one single element, and maybe I'll put parentheses around here to be extra clear. And well, we have this is equal to 0 plus the exact same elements. Okay, but here notice that we have an element, we're adding with its additive inverse. So we're going to use the additive identity axiom as well as the neutral element axiom on the right hand side. And that should give us a times negative b. Well, this guy is just plus 0. And this is equal to negative of ab on the right hand side, but again we can just ignore this 0. So we really get a times negative b is equal to negative of ab. And notice we had to use this technical argument of having to add the additive inverse on both sides when we want to move an element over to the other side. Maybe that's something you can show as well. So another exercise is to show that if you have a plus a b equals a c, then this is equivalent to a being equal to negative b and then plus c. And another exercise as well, which is pretty much just a corollary of this fourth property here, is to show that if you have a negative a and then negative b, that's just going to be equal to a times b. And the key with this one is to show that if you have negative of the negative of an element, that's just equal to, well, the element itself. It's a nice exercise to do, it's not too tricky. Okay, and that's all for this video on some basic ring properties. So probably not too much of an insightful video, but it shows you how you can use the axioms to deduce some very basic properties that we already know and love from primary school. So that's all for this video. Have a wonderful day, and I'll see everyone in the next one.